to introduce the next speakers for our session, the next generation of semiconductor technology. We have Chris Miller, who's the author and New York Times bestseller of Chip War, The Fight for the World's Most Critical Technology, which won the Financial Times Prize for the Best Business Book of 2022 and was also shortlisted for the Lionel Gerber Prize. He's also the associate professor at Fletcher School at Tufts University. And we're also joined by Ahmad Bahai, is a senior vice president and CTO of Texas Instruments, responsible for guiding breakthrough innovation, corporate research, and Kilby Labs. He is also a professor of practice at MIT. Please join me in welcoming Chris, Ahmad.
Well, our task today is to discuss semiconductor manufacturing, and it's already obvious who is the expert and who is not on this subject. So Ahmad and I thought we would start by having me talk about some of the history, since I do know something about history, and then engage in a bit of a conversation about the policy landscape in the United States related to semiconductor manufacturing. Picking up in some ways on what Professor Huang was talking about in the previous discussion, one of the big trends in the semiconductor industry over the past several decades has been a trend of internationalization of the actual manufacturing of semiconductors. And if you look at the market share of chips manufactured in the United States, you'll find a real substantial decline over the past several decades, from roughly a third of chips being made in the US 3 decades ago to around 10% today. And there's a lot of differentiation depending on which types of chips you're talking about, and we can get in to some of that. But this has been an issue of concern both to businesses and to policymakers for a couple of reasons. One are the geopolitical factors that were alluded to in the previous conversation. One of the countries that has played the biggest role in building up its own chip manufacturing capabilities is, of course, Taiwan, which produces today around 90% of the most advanced processor chips. But in addition to that, there are questions of innovation. Can you have manufacturing innovation if most of the manufacturing is actually happening offshore? Can you build the workforce you need for the next generation if many of the manufacturing jobs are not happening, are not being hired for in your country? And so this is a conversation that's been growing in, I think, focus both in industry and in government over the past several years, and reached an inflection point in about 2 years ago when the CHIPS Act was passed. And the CHIPS Act in the US is actually mirrored by industrial policy efforts in other countries. The European Union is in the process of finalizing an EU CHIPS Act. They don't get very high scores for innovation in terms of their titles, having directly copied the US version, but nevertheless, they're doing something similar. And then with less publicity, Japan is spending very large sums of money, especially as a share of Japan's GDP, on its own semiconductor manufacturing ecosystem. And then there are other countries as well that have played a smaller role in the chip industry in the past, like India, which are now also putting really substantial resources and attention into trying to attract more manufacturing of semiconductors. If you look at what the CHIPS Act is trying to do, there's two main prongs of effort. The first is to provide incentives for manufacturing in the US, and the rationale for this is that there are pretty good studies done of the cost differential between producing in the US and producing in other countries, and it depends again on which types of chips you're producing. There's a lot of variation, but ballpark, it's 20-30% more expensive to produce in the US across different types of semiconductors. And so one of the goals of the CHIPS Act is to provide some incentives to bring down that cost differential, which has been one factor among several factors as to why a larger share of chip manufacturing has been happening in Taiwan, in Korea, in China, and elsewhere. The second major prong of the CHIPS Act is money to go into R&D and workforce development. I think that's where we'll probably spend a not insignificant portion of our conversation today. And the rationale behind these funds is that, first off, if you want to build manufacturing in the future, you need a good workforce behind it. And that's something the US has actually had a very good track record of developing, but is still important today. And on the R&D front, the chip industry is in some ways unique because it is so R&D intensive, and because the R&D has produced such extraordinary results. I like to just put Moore's law in the context of every other industry in the history of in the history of human existence, and there's nothing else that's come close to the extraordinary progress of Moore's Law, a doubling of capability every 2 years. Imagine if airplanes flew twice as fast every 2 years. Actually, I asked this question to an audience yesterday, and someone told me if it was true that airplanes flew twice as fast every 2 years, and that lasted for the duration of time we've had Moore's Law, airplanes would be flying 6 times the speed of light by now. I haven't calculated that myself, but it sounds roughly right, which is why the trajectory of the chip industry, from the first commercially available chip having 4 transistors on it to the chip inside of your iPhone having plus or minus 15 billion transistors, has been so extraordinary. And so R&D is the critical factor going forward. Can we keep Moore's Law alive? Over what time horizon? And if we can't keep Moore's Law alive, then what comes next is the other big question. And so the CHIPS Act is putting a lot of money into R&D, trying to support these efforts. And maybe as a final point, this is in some ways a new initiative for the United States, the government trying actively to support the chip industry, but in other ways it's a return to some of the history. We were talking over lunch about Semitech, an effort in the 1980s and early 1990s by the US government to put money into certain R&D efforts into the chip industry. But if you wind all the way back to the earliest days of the chip industry, government was there from the earliest stages. The first semiconductors that were ordered from companies like Fairchild NTI were used in government systems like the Apollo spacecraft, designed just on the road from here, which had some of the earliest semiconductors ever invented in its guidance computer, and also a whole variety of defense systems as well. So this is the policy landscape in which manufacturing decisions are being made today. So it's a new landscape in many ways, although one that has echoes in history. So perhaps I could turn the conversation back to you with a question maybe to start, which is, as you look at this new policy landscape and the CHIPS Act and just the general focus on manufacturing, is this the right approach? Is it going to be enough to change the trajectory of chip making that we've seen over the past several decades?
Yeah, thanks, Chris. A lot of good points you already raised. To answer this question, maybe let's put it in the context of what's happening in semiconductor. I really think that semiconductor technology, the race of this century, it's a strategic value, it's economic value, it's national security, and what's happening around us. Just to give an idea, it took us 60 years in semiconductor industry to get something about $500 billion business. And the expectation is that in the next 6 years, it's going to be more than $1 trillion. So that's the way that's going. I mean, just look at what's happening around you. A thermostat used to be just the two metals and touching each other and thermocouple. Now there is like $30 of semiconductor content, from Wi-Fi to AIs in a doorbell and everything else you can imagine. So definitely we see a lot of room for growth in terms of innovation, in terms of opportunities, market, and strategic value. As we talked earlier before this meeting, actually, manufacturing is a big part of semiconductors innovation. A lot of vectors converged to the point that we offshored a lot of manufacturing capabilities. Part of it was that this massive amount of investment we need for leading edge technologies requires kind of a lot of money, a lot of effort behind that, and obviously, companies who are working on leading-edge technologies or using that decided that maybe foundry business is the right model for them. But I think a lot of innovation we see and differentiation in semiconductor really is on manufacturing part of it, on the new devices, on how to optimize manufacturing. So by offshoring it, we really kind of like deprive ourselves from some of these in the US. So I think foundry business has its own merit, especially for leading edge. But we need to have that in a way that we can have a strategically kind of create the right competition and take advantage of that. When it comes to larger nodes, manufacturing also is very critical. In fact, there are a big chunk of semiconductor market that doesn't rely on leading edge nodes. These are things that, we are living in an analog world. Everything around us is analog. What you see, what you hear, what you smell, what you touch. These are analog, so before even getting to a digital processor, there is a lot of electronics in between. And these are all the electronics that usually don't require leading edge, but manufacturing can play a big role as far as differentiation and innovation and cost and performance. things like MEMS, sensors, photonics on silicons, a lot of advanced data acquisition, power management, high voltage in electric vehicles, and so on. So there is such a wide range of technologies that requires different manufacturing capabilities. So this incentive to bring manufacturers or promote manufacturers different parts of the world is a great thing. I think US, of course, is putting CHIPS Act money together. Europe is the same thing, Japan, China, all over. So not at the cost of starving other parts. It's just creating a competition worldwide. I think that benefits everybody because semiconductor is going to be around for foreseeable future. It's going to make a big impact. A lot of electromechanical system or electromechanical systems are replaced by chip-based systems and MEMS. And as you know, one of the projects that we have, actually this projector that is shining, most likely there is a chip from TI that has 2 million tiny mirrors on a single chip. And these mirrors are flipping billions of times in their cycle. So you can see that it can go so many directions as far as enabling new capabilities. A typical car used to have like a $200 to $300 silicon content. Today it's about $2,000 silicon content. So we see this trend, it keeps going, and having manufacturing advantage as far as innovation is important, but it has to be a global competition to make sure that we get the best talents working on the best technology.
And when you look at the workforce in the US, one of the things that some players in industry say is, well, we've got our workforce overseas, they understand how to work in our facilities as we got them structured, and so it's hard to find workers who are capable or willing to work in a fab. Is that something that you've found to be true at TI, or how would you assess more generally the state of the workforce in the US?
Yeah, definitely there are two elements that contribute to the workforce challenges. One is that we didn't train enough people at every level, from technicians who run the fab all the way to PhDs who are doing R&D on the advanced process and devices. And also we didn't promote manufacturing as much as we used to. So these two elements came together and created a situation that we need to train more people and incentivize more people. Another trend that kind of worked against this is the fact that some of the new software, exciting areas of software, attracting a lot of talents, and people prefer to go to like some areas of early gratification rather than having like many physics and mathematics and chemistry courses before you can touch a semiconductor. So we need to work on curriculum. I think places like MIT, which was one of the main bedrocks of the semiconductor industry, how to create this early gratification by exposing students to final solution of products. I mean, I remember when I was a high schooler, I really loved to work with these transistors with 3 pins, that is emitter, collector, base, and now you design a system with billion transistors and you don't see one. You sit in front of computer and then something pops up and then you don't see what's going on beyond that. But if we can change this slightly, is to incentivize top talents to work on some of these fundamentals is important. So there are 3 elements to that. One is training people at every stage of the expertise, from technicians to PhDs and domain experts. Second one is that make it, again, kind of like an exciting area for us so that we can spend time. And I'm really glad there is so much attention. Semiconductor, I don't have to explain to my family what do I do for a living anymore. So now semiconductors everywhere. President holds the wafer in his hand. So it's kind of like, it's exciting. And the third one is that we really need to create a global competition for labor. Again, one of the strengths of US economy and US market is that you can bring the best talents here and leverage that in short term while you are building the foundation for the training new talents down the road.
And you certainly see that historically. You can go back to the early days of the chip industry and ask who was it that was driving both company formation when it comes to startups, but also new innovation. And it's a lot of people who were born in America, but also a lot of people who came to the United States from the very, very earliest stages. But I wanted to pick up on the question of making semiconductors exciting again. I don't know what the right acronym for that is, but it seems to be a really important trend because, as you say, there has been, I think, a trend, probably not only at places like MIT, although I think if you chart the number of people at MIT studying electrical engineering versus computer science, I think you see some pretty clear trends there. But more generally, culturally, if we went on the street and pulled people to name 3 tech firms, I think they would probably name Google, Facebook, and Amazon, which I suppose are fine firms, but it strikes me that what you're doing is a lot more fundamentally interesting and important than what happens at social media companies. And so I do worry that culturally we've sort of misdefined tech as involving the consumer internet rather than the actually really cool stuff that undergirds it.
Yeah, that's kind of sometimes a bit frustrating for us in semiconductor because in some meetings on a daily basis, I have tens of PhDs from chemistry, physics, device, electronics getting together just to shave off half a penny of cost of a chip. And you don't see it on a device. I mean, when you go to stores, you don't see TI or other semiconductor companies. You see the names that you mentioned. Of course, they are consumers. So I think there are two elements to that. One is the market trend. Of course, if the compensation for a software engineer AI is twice as much, which used to be, then there is so much you can do. But market trends over time balance themselves. And if AI is as good as it's promising, it has to reinvent itself. So you don't need as many AI engineers, right? I mean, so AI is going to create more AI IP. But also, as I said, I mean, in semiconductor industry, a lot of universities, and I've been involved in many universities, still we have a little bit of traditional curriculum of, you have to take so many courses, so many years before even touching something that really feels like you're making a difference, unless you're fascinated by theory and some of the aspects of science and technology. But if we can change that and expose students or technicians to the final thing that, okay, you can make a robot, or you can make a satellite which kind of just is like so tiny you can launch it from the campus here. You don't need to go to Florida or Houston. Or you can design a system that can connect to your smartphone and do something unique on education. Then that kind of brings a new crowd of people who can see the impact, who can enable. And frankly, the way that the industry in semiconductor is thriving, we are getting so good at providing those Lego blocks that really we can enable that. It's just we need to have a different approach to incentivizing or inspiring people to get into this field. Fortunately, we see already the pendulum is swinging in the right direction. We see a lot of attention now in semiconductor, and people would love to learn more about it. And the other angle is that some of the manufacturing of semiconductor, especially front end of the line, is so automated that you don't need as many resources as before. You need to have people who are really good at highest end of the design and automation and manufacturing automation. But manufacturing is a big part of innovation in this value chain, and we cannot ignore it.
Well, and it is interesting the number of employees inside of a fab, a manufacturing facility. I think people often hear about manufacturing being offshored and think, well, it must be a labor cost differential story. And actually, in semiconductors, that's not really the case. There's a relatively small number of workers, and in Taiwan or Korea or even in China, they're pretty well paid. But if that's true, then well, what does explain the cost differential?
I think it's more like a talent, access to the talent and the stability of that, because in a typical, let's say we have most of our manufacturing in the US actually, and we are quite price competitive worldwide. So these are 300 millimeter fabs. They ship billions of chips a year. And there are not that many people running around. Robots are pretty much handling most of the wafers because there are many advantages to that as far as the throughput and reliability and all that. So it's really access to the talent and training the right people through this collaboration with universities. I mean, I saw the numbers from MIT campus that the number of students, I don't remember if it was graduate or undergrad, but the number of students registered in CS is larger than the entire engineering. So the question is, are we training the right people for semiconductor manufacturing and capabilities in top schools and top talent? So that justifies that. When it comes to back end of the line, it's a totally different story. The packaging and test and all that. So today, it's a lot more labor intensive because it's more manual much more manual than front of the line. But also that also is going through a major disruptive changes in the sense that now we are seeing a lot of automations is coming to the back end of the line, and we see opportunities for onshoring some of those.
Well, I'd be interested to hear you talk through a bit more about what's changing in packaging. Just to put it into context, as Moore's law gets harder and harder to continue, there's more focus on packaging chips in different ways for power efficiency, for data transfer speeds, for all sorts of other potential performance improvements. Does the United States have a advantage as we move to more focus on heterogeneous integration? Or is the fact that most packaging is actually happening today in Southeast Asia, in Taiwan, in China, does that actually put us at a disadvantage in terms of capitalizing on those trends?
Yeah, it's a very good point. Actually, this 3D opportunities in semiconductor industry is a unique disruptive technology that is giving us a chance to bring some of those packaging back end of the line to US, because they tend to be a lot more advanced. They are, in some cases, like wafer bonding and hybrid bonding. It's very similar or more similar to front end of the line, so you can take advantage of automation even more. And also, it has a lot of device interconnect, substrate, material challenges. So I would say it's a point of disruption in semiconductor back end of the line, and it's perfect opportunity for us to push the innovation to the next level and bring some of those technologies in-house. Because the traditional technologies on back end of the line, which, as I said, is very labor intensive, it's always a matter of economy that is driving that. But these new trends on 3D heterogeneous, in many ways, is giving us an opportunity. For example, for last 30, 40 years, as you pointed out, Moore's law was almost a single trend. If you cannot solve a problem today, wait until the next node comes. It's faster, denser, cheaper. It's going to solve the problem. And for that reason, almost all of the industry, in terms of talents and investment, was focused on what's the next node. Now that is coming to almost like an end and getting to the point that we don't see the advantage of scaling as much in terms of cost, in terms of power consumption, then there are many other vectors, new materials for high voltage, new materials for power management, for RF, for MEMS, which are not taking advantage of this shrinking and scaling of the Moore's law, are popping up as an opportunity. And those technologies need to coexist in a chip. And that is the genesis of the heterogeneous integration. Gives us a chance to diversify technology, or they call it democratize technology, in a way that you can bring more pieces, more innovations, and bring the whole integration to the next level of automation and opportunities for differentiation.
And it's worth noting that in the context of the CHIPS Act, there's a separate National Advanced Packaging Program, I think you're getting the title wrong, that's focused specifically on this very question. If you look at the incentive side of the CHIPS Act, so $39 billion over the next roughly 5 years, going to be given to different firms for new facilities, plus a big investment tax credit, which is probably just as large in dollar terms as the incentives. To what extent is this going to change the decisions of companies on the micro level, and to what extent will it, at macro level, impact the share of chips that are manufactured in the US versus in other countries?
Yeah, I can comment on technical aspects of it, not on the political, because there are some conditions attached to that CHIPS Act funding, including like having a child care on site or not doing buyback of stock. So those have impact on companies to make a decision they wanted to leverage that or not. So that part I'm not very good at that. But on the technology side of it, I would say the incentives for manufacturing makes an impact. I wouldn't consider that as a handout from government to start something from zero. But if you are planning or you already have some manufacturing capabilities, helps you a lot to expand it, to make it more competitive, and to innovate on that front. In TI, we are already on our roadmap toward 6 new 300 millimeter fabs with the capacity of more than 100 billion chips a year, all in US. And we see that we can compete with every company anywhere in the world at cost and performance, including China, including Southeast Asia, because it's about the innovation and manufacturing and design and the whole ecosystem. So that helped a lot. So that's the $39 billion part of it. Then there is another 12 billion, 11 billion that is more like R&D side. That's still under discussion, how to leverage universities, industries, and government in the most efficient way. That's kind of like Semitech type of thing. And I can see that there's a lot of good proposals on the table. Again, the challenge is that even if you have the money, where do you get the talent and resources right away? And if it's a central organization, how do you compete with industry to recruit talents? because industry has other leverages, stock options and things like that too. So there are still some unknowns, and that $11 billion is going in the right direction, but I would say the race is on, and the race for recruiting top talents is now global.
Well, it's interesting if you look at the history of Semitech. I think at best it was a mixed picture as to its efficacy. Bob Noyce, who was in charge of it, was one of the people credited with inventing the first integrated circuit, was the president of Semitech in his early years, and he spent half of his money trying to rebuild the U.S. lithography industry and failed. And he passed away just kind of in the final stages of that effort. It was really the only thing in his life that he failed at after a string of successes before then. And so I think it is a cautionary tale in some ways of, well, money alone isn't necessarily going to solve problems, make an impact unless it's structured in the right way. Can you talk a bit about what the venture landscape looks like and ways that it might need to change to?
Yeah, the good sign of it is that with this CHIPS Act and this attention to semiconductor is changing. To your point, even the access to EDA, these EDA licenses are super expensive. Even for you to have a tool to design your chip for your idea, that's very prohibitive. So there's a lot of activities going on how to facilitate access to the tools in an environment that people can use it for prototyping. Again, lab to fab, access to some capacities to build your chip, access to packaging resources to package your chip. So these are initiatives that really is going to lower the barrier for startups to get into this, and for VCs to get incentivized that you don't need to buy a design tool that is $1 million by itself. You can have access to that through other channels. So a lot of initiatives in the right direction is happening there, and it's quite promising. But the question is that the timelines and the dynamics of the market that you need to be mindful of.
Well, that is an optimistic note to end on. Thank you very much, Ahmad, for this conversation.
Thank you.